Hello everyone, welcome to another webinar from our Rocky in Action webinar series. My name is Taina Gabardo and I am part of the technical team of Rocky DEM. Today we are going to make a quick presentation about mills and show how can we use DEM simulations to improve this equipment and operating conditions. Let's start defining what are mills. Mills are equipment used in the mining industry to reduce the granulometry of ores by grinding, crushing, or cutting. These equipment are normally rotating machines that contain steel balls and ore. They can be classified as SAG mills, semi-autogenous grinding mills that are usually a first stage grinder, AG mills, autogenous mills, that use a rotation drum to throw larger rocks of ore in a cascading motion, which causes impact breakage of larger rocks and compressive grinding of finer particles. And we have also ball mills that grind material by friction and impact with tumbling balls. This is the geometry of the mill, where we can see the lifters and the plates. As the mill operation is normally constant, it is not feasible to perform a comprehensive experimental design. So, Rocky has proven to be very helpful in such cases by enabling increased process insight and also evaluation of a large number of possible solutions. In today's session, we are going to show how can we set up a DEM simulation of a mill and do some post-processing analysis in Rocky. We will begin turning on collision statistics. Then we will import the geometry of the mill and duplicate it to create a reference one. Next, we will set the rotation motion frame. We will configure material properties and material interactions. Then we will create two particle groups to be used and set the volume fill. Once the setup is done, we run the simulation. Then we will show how to color particles by certain properties, like velocity. We will evaluate the surface wear by creating a custom property. Next, we will use particle trajectories to understand the effects of wear. And finally, we will investigate the total power to run the mill. Now I'm going to walk you through the simulation workflow and highlight some parts. We will start our simulation by defining the rolling resistance model in the physics steps and also by reducing the numerical softening factor. The other models are default. Next, at the modules tab, we will select boundary collision statistics and then enable intensities. In the geometries panel, we will import the geometry, save the simulation, and we will use the unit as millimeters. Then we will create the rotation motion. The mill will start with 3 seconds of angular acceleration and then a constant angular velocity of 10 revolutions per minute will be applied. After creating the motion frame, we need to assign it to the geometry and also add a wear model to the lifters. We will use the Arcard's law. When analyzing wear, it is important to set the geometry parameters correctly, especially the triangle sign. This will define how refined the mesh will be for computing wear. For this simulation, we will use a triangle size of 0.1 meters. And now you will see in details this refined mesh. Next, we will create a duplicate of the mill. Next, we will create a duplicate of the mu to serve as a reference. We will set the enable time as 1000 seconds. So this reference won't suffer from any wear effects. For the materials step, we will create two new materials. One for the ore, rock material, with density of 2800 kilograms per cubic meter, and another for the grinding media, steel material, with density of 7800 kilograms per cubic meter. Next, we need to update the material interactions. We will only update rock and rock interactions and rock and steel interaction. For the particles step, we will create two sphere-shaped particle groups with rolling resistance. The first group will be rock particle with rock material, and it will have a particle size distribution as follows. The rolling resistance will be 0.35. For the second group, it will be called steel particles with steel materials, and it will only have one size. The rolling resistance will be 0.35 as well. Next, we will create a volume fill input constrained by the mu geometry with 32 tons of rock particles and 8 tons of steel particles. We need to update the seed coordinates close to the bottom of the mu and also enable the use geometries to compute with the mu geometry. Then we will enable the collect context data option at context tab. And for the domain setting, we will define a Cartesian periodic domain with the z direction to recycle particles that live on one side back into the simulation from the opposite side. Finally, we will define the simulation duration, output frequency, wear time, and we will start the simulation. Once the simulation finishes, we can start post-processing. We will begin by coloring the particles as a function of the absolute translational velocity. You can observe high and low speed zones. Next, we will create a custom property called radial displacement to evaluate the wear on the mill surface. We will enable displacement X and Y. We will name the property radial displacement with the output unity as meters. We will create the expression of the radial displacement. And finally, the new property is created. We can then observe the wear on the surface of the mill. we'll start from plotting the worn surface at 15 seconds, as you can see in the tail. And again, at the end of the simulation. We can also compare with the mu reference. We could also analyze the worn geometry by exporting it out of rock and view it in a CAD or other 3D graphics program. Next, we will analyze the particle trajectory. We will start from 15 seconds, display 25 output frequencies with 5 as particle stride. So select 15 seconds, update particle selection. We can then display it as a function of the absolute translational velocity and hide the particles. Next, we will increase the starting part to 35 seconds. We will then return to 15 seconds to compare with 35 again. It is interesting to evaluate that the particle trajectory, it changes as time passes by. You can see that the cascading effect is reduced because of the worn surface. Finally, we will compute the power to run the mill. Select the mill geometry at the data panel and then curves at data editors. And then we will create a time plot with power. We will change the output unit to kilowatts. And then you can observe that the power to run the mill is approximately 1100 kilowatts. So the results from the simulations can be critical for driving engineering design and prospect operation issues. They will help to optimize the geometry of the lifter, find the best height and inclination, evaluate the surface wear of the mill over time. These results will allow you to find ideal operation conditions. They will help you to predict low speed or high speed zones and volume fraction. They will help to see how the material flows inside the mill and also the effects of the wear on the particles trajectories. And they will also compute the power necessary to run the mill. Finally, they can predict the breakage of ore, the impact velocity, the collision frequency, and much more. Well, that's the end of our Rocky demonstration about mills. Now, I would like you all to attend our next 15 minutes webinar that will take place on the upcoming weeks. The next one will be on November 3rd about excavators. See you there, and thank you everyone for attending our today's session. Please connect with us through one of our channels. And if you have any question, please send to us in the chat. Thank you everyone, and see you next time.